Webster's stunning.
Someone does not speak Hebrew. Okay, we are ready for this as well. I'm happy to introduce Oren Salzman, who is coming to us from Carnegie Mellon. Oren did his undergrad studies at Technion, his master thesis and PhD here at Tel Aviv University. Full disclosure in my group. And about a year and a half ago, Oren went to presumably the largest academic center in robotics in the world, to Carnegie Mellon, and you and I will hear what he has been doing since.
Okay. Thank you for the kind introduction and for attending the talk. So I don't need to give a bit of background about myself. Daniel already gave it. I just want you to notice the difference between the nice sunny pictures of the Technion in Tel Aviv and the snowy picture of Carnegie Mellon University. While we had the storm in the weekend, my wife was struggling with minus 20 degrees in Pittsburgh. So just to put things in perspective. It looks sunny. This is this is before the storm, but it was not pleasant. So let's dive into robotics. From the first robot system, this is Shaky, developed at Stanford Research Institute, to modern robots that clean our house and provide means of transportations for lazy cats, all the way through warehouse robots, where fleets of robots need to coordinate their motions while moving pods from one area to the other, and all the way through modern robotics, where robots assist in performing complex surgery. A common theme is the requirement of, or the ability to autonomously plan and execute motions. And what I've been doing in the past years is trying to address the computational challenges that arise while planning for robotic systems. So my research lies on the intersection of computer science and robotics, and I've been motivated by this key insight that to solve these types of problems, we need to revisit traditional tools developed in computer science. So this means that we need to A, understand the specific challenges that arise from this domain of robotics, and B, address these challenges by introducing new algorithms, paradigms, and tools to address these challenges. So what is the motion planning problem? This is a picture of Herb, the flagship robot of the personal robotics lab that I've been involved in. And he needs to plan the motion of his arm from below the table to above the table while avoiding intersection with the obstacles. In this case, it's a table. We're given some description of the environment. In this very simple case, it's the table. And we need to plan the motion for Herb. This is the fundamental problem that we're trying to address in this context. And what I want to do in this talk is, first of all, establish some common language. I'm going to give a very brief introduction, a crash course on algorithmic motion planning. And then I want to describe some of the interesting challenges that arise from this domain of planning for robotic systems. What I want to do is, first of all, talk about the general challenges that are common to many robotic systems, and then look into one of these challenges and describe one of the algorithms that I've been working on to address this challenge. Then I want to dive into some domain-specific challenges for specific applications, like assistive robotics, and describe what happens when we look into these specific domains. And again, I'm going to go into one of the algorithms that I've developed to address these challenges. So let's start with a very brief introduction. If something's unclear, please ask. When we study the motion planning problem, the robot operates in some physical space. This is called the workspace. In this case, it's a very simple two-dimensional workspace with some polygonal obstacles. And the robot here is placed in the workspace. In this case, it's a very simple robot. It has a fixed base and two joints which can rotate. So it can form some kind of motion like this. And each position of the robot in the workspace can be described as a d-dimensional point in what's called the configuration space. Each point here is called a configuration. In this case, in order to describe the position and orientation of the robot, we need to specify each one of the angles of the robot's joints. And this corresponds to one point in a space called the configuration space. Now, the configuration space has obstacles. Here I color-coded each one of these obstacles corresponding to the robot intersecting with one of the obstacles in the workspace. And now we can say that all the white configurations here correspond to placements of the robot that do not intersect the obstacles. This is called the free space. A final notion that we need to define is the number of degrees of freedom. So in this case, in order to uniquely define the configuration space, we need two parameters, one for each one of the robot's joints. We'll see examples where the configuration space is very high dimensional. And now we can restate the motion planning problem. We're given a robot, a description of the robot, and we're giving an initial and final configuration of the robot. And we need to plan a collision-free path. In this case, it's the white motion that corresponds to the motion of the robot in the workspace where it does not collide with obstacles. And what's important to note here is that the free space is not part of the input. We're given the workspace as part of the input and the description of the robot, but we don't have any idea how the obstacles in the configuration space are structured. Now, this was a very simple example where both the workspace and the configuration space are two-dimensional. In practice, robotic systems are very high-dimensional. This is another picture of Herb, the robot that I mentioned earlier. Each one of Herb's arms has 7 joints. So each one has 7 degrees of freedom. It's bimanual. It has 2 arms. In addition, its base can move. So Herb has 16 degrees of freedom. The workspace that Herb operates is the physical space. So it's a 3-dimensional space, while the configuration space is 16-dimensional in this case. Proteins can be modeled as robots, and these are systems with hundreds of degrees of freedom. So this just emphasizes the difference in dimensionality between the workspace and the configuration space where we're actually doing the planning. Now, the first efforts in the motion planning community, late 70s, early 80s, were aimed in order trying to find an explicit representation of the configuration space. However, the problem is p-space hard with respect to the number of degrees of freedom, so solving this problem analytically is hopeless in some sense. The problem is intractable. And even finding an optimal path in 3D is an NP-hard problem. So we have to resort to other methods. A common method from mid-90s, it's called the roadmap method, or the probabilistic roadmap method. And here we're trying to approximate the structure of the configuration space using a graph. And vertices in this graph are going to be configurations. And edges in this graph correspond to local motions of the robot between these two configurations. So let's try to visualize this. Let's assume that this is a configuration space, and we sampled the space. Note that some of the samples correspond to configurations where the robot is in collision with the obstacles. So what we're going to do is we're going to call what's called a collision detector. This is some geometric testing, checking if the robot intersects the obstacles in one specific configuration. And we can do this in the workspace. So we can throw away all configurations that are in collision. And now we can connect each configuration to a local neighborhood of close-by configurations using some nearest neighbor data structure and some local planner. And again, some of these configurations corresponds to local motions where the robot intersects the obstacles. So we're going to call the collision detector again and throw them away. And now we have a graph that is embedded in the free space. And any path planning algorithm that plans a path in this graph, like Dijkstra or A*, computes a path that corresponds to a motion that the robot can take that is collision-free. And this is a meta-algorithm that has been used probably since the late 90s. What I want to do now that we established this common language is talk about the challenges that arise when planning, when applying such techniques. So the first question that we need to ask is, how do we sample in this space? So in my specific example, we sample uniformly, but especially when we want to converge to high quality solutions, to solutions where the robots takes the minimal cost of path, then we need to do something more sophisticated. In this example, we add kinodynamic constraints. So what can we do when the robot has also velocity and acceleration constraints? That's one question that we need to ask. How do we compute nearest neighbors in this domain? Do we use any nearest neighbor data structure, or can we use data structures that are specifically tailored for the type of questions that we ask in this specific domain? If we're talking about nearest neighbors, then it means that we have some underlying metric. So an interesting question that we need to answer in this domain is, what is the right metric to use for different robotic systems? This is recent work where we studied metrics for multi-robot motion planning. So each configuration is the placement of multiple robots in the configuration space. Another question is more on the theoretic side. What are the theoretic properties that we have to that ensure convergence to high quality solutions? Once we have these theoretical properties, how do we use them to efficiently compute high quality paths in this domain? Yeah. Okay. We can try to find a path, which is the way I presented the problem earlier. But we can try to optimize for some criteria: minimal time, minimal execution time, minimal energy, maximum clearance, so some safety from the obstacles. So we have, I assume that there is some optimization criteria, and we want to find a high quality solution. Maybe converge to the optimal solution, or to some finite approximation over the optimal solution. Another interesting question is, if we spend a lot of preprocessing time in order to produce a data structure, one of these graphs or roadmaps that encompass the structure of the configuration space, what if we need to compress them because we have some limits on the memory on board of the robot? So this is a very interesting question on compression in the context of robotics. And I mentioned that we can run any path planning algorithm, A-star, Dijkstra, but is that the right thing to do? And I want to dive into this specific problem of how to search a graph, because I assume that A-star, Dijkstra is something that it's common, and I don't need to introduce any background there. And this algorithm that I'm going to present here, this is going to be the next section of my talk, really underscores how, if we take an algorithm developed in the absence of the robotics domain, it's just unsuitable, and we need to understand the subtleties of this domain, and when this allows us to present much more efficient algorithms. So searching a graph, and this is going to be the next part of my talk. So the algorithm that I'm going to describe is called Lazy Receding Horizon A-star, or LRA-star. This is recent work which we just submitted to ICAPS, the International Conference on Automatic Planning and Scheduling. And to understand why we need this specific algorithm, we need to understand what are the computational bottlenecks that arise when planning in the context of robotics. And here, edge evaluation is considered the computational bottleneck. We have an edge, and we need to understand the cost of traversing this edge. And this cost corresponds to testing if the robot intersects obstacles or not while traversing this edge. But it can also encompass computing, say, stability constraints. If we have a humanoid robot and there's no obstacles around, but while taking this motion, the robot will topple over, then we need to compute these stability constraints. It can also encompass physical simulations. So I'm going to talk about edge evaluation, and this is a computationally complex operation. And when we're looking at high-quality solutions, this typically involves computing dense roadmaps with many edges. In some cases, report that 99% of the planning time was devoted to edge evaluation. And the idea here is to use what's called lazy edge evaluation, to delay edge evaluations until absolutely necessary. And this idea is both applicable to motion planning in the continuous domain, which I'm not going to talk about, and to path planning, which is what I'm going to talk about now, planning on a given graph. So let's try to formalize it. We have two configurations, and we have a cost function which maps the cost of traversing an edge. And if traversing this edge corresponds, say, to intersecting with an obstacle, then the cost is simply going to be infinity. And we have two assumptions here. The first one is that computing this cost is computationally expensive, and we want to avoid it. However, the second assumption is that we have some additional tools we can use. Typically, there exists some efficient to compute lower bound estimate of the true cost. So let's try to visualize how this looks like. This is the same picture that we had earlier with the robot, and we want to estimate the cost of moving from this configuration to this configuration. And this corresponds to moving along the straight line in the configuration space. In this case, we know that this motion is going to cause the robot to intersect with the green obstacles, so the cost is going to be infinity. And this involves this complex geometric testing of computing the collision between the robot model and the models of the obstacles. However, if there was no obstacle here, the angular distance, which corresponds to the Euclidean distance in configuration space, is a very efficient to compute estimate on the true cost. And if there was no obstacle, that would be the true cost. And the key idea that we want using this paradigm is to use the lazy estimate to guide the planner when and where to compute the real expensive to evaluate cost. Now, this idea is not new by any means. Almost from the early days, so I mentioned that this approach dates back to mid-90s to 96. So almost immediately after some variants of this idea of using lazy computation was used. And in the recent years, there's been much more work on using lazy computation. And this is because the community has shifted to looking into high-quality solutions, and this problem has been accentuated. So I'm going to briefly describe two of these algorithms and then demonstrate that there's two instances of a family of algorithms. Yeah?
Is the assumption that the edges have, that the total cost is the sum of over edges correct? I mean, you may need to decelerate to zero, or you may not decelerate to zero.
That's a great question. That's a great question, and I'm actually going to show an instance. I'm going to show, actually, briefly go over two instances where we have a graph, and this assumption does not naturally hold. So one of them, the Bellman condition, doesn't even hold. We'll get to that. And the other, we don't want to find the minimal. The metric that we're using is over paths and not over edges. So you're right that in many cases this does not hold. For the sake of this talk, just to keep it self-contained, this problem, you can assume that even we're talking about Euclidean distances and the sum of a path is, but it's a great question. So let's look at the first algorithm that I want to describe, called lazy SP. And we're given some graph and two vertices on this graph, and we want to produce the shortest path along this graph. And how does this algorithm work? Super simple. We're going to search this graph without performing any edge evaluations or collision detection, and we're going to obtain some path. Now this path, if it's collision-free, it's going to be the shortest path. If not, then it corresponds to some edge being in collision with the obstacles. So let's go over the edges one by one and test, are they in collision? If the answer is yes, then we can report success. And the answer is no, then we need to update our data structure, our graph, and search it again. So let's sort of visualize how this looks. I'm going to use this color-coded scheme where dashed blue edges correspond to edges evaluated using our estimate of the true cost. And you're going to see in a second that solid blue edges are going to correspond to edges evaluated using the expensive to evaluate cost. So the first thing we do is we compute the shortest path tree from the start to the goal. And notice that because we're using a lazy estimate, some of the edges correspond to intersections with the obstacles. And the first thing we do is we compute the shortest path from start to goal. In this case, this path is invalid. We're going to start by evaluating edges along this path. And I'm color coding this in solid blue. And we see that we realize that one of its edges corresponds to an intersection with the obstacles. And what happens here is that we realized that the lazy estimate did not guide us correctly. And we have this whole subtree emanating from the edge that we found to be in collision, which we need to recompute, or I'm going to call this a rewiring operation. So now, to this node, we're going to get to him from here. And we corrected our shortest path tree, again, using our lazy estimate. Now we're going to run the same algorithm again. We found another shortest path from start to goal. In this case, it's collision-free, and we can terminate. Super simple idea, highly effective in practice. Let's talk a bit about the properties of this algorithm. To do so, I need to introduce the notion of what's called edge optimality. So we say that an algorithm is edge optimal if, under some set of constraints or rules, this is a computational model that we're looking at, if any other algorithm has to perform at least the same number of edge evaluations on any given graph as this algorithm. And what we've shown in two different papers is that LazySP, the algorithm that I just described, is edge optimal under some deterministic model and probabilistic model. So it looks like LazySP is the best that you can hope for, right? It's edge optimal. But we're not trying to optimize for edge evaluations, but we're trying to minimize the total computation time. And this is just a proxy. So let's look at the cons of this algorithm. Every time we found an edge to be in collision, we have to do this mass rewiring of the subtree emanating from the edge that we found to be in collision. And we can do this efficiently by reusing information from previous iterations. But still, the algorithm spends a lot of time on graph operations and not on edge evaluations. So this is one algorithm. Let's look at a different algorithm called lazy A star. This is a very natural variant of A star. And it runs exactly an A star algorithm, but it computes the true cost of an edge only when the search believes that the edge lies on the shortest path to a node. So let's try to visualize this. I'm going to use the same color code. So we're going to start our search from the start. And the dashed blue edges, again, corresponds to edges evaluated using the lazy estimate. And we're also going to use an orange region. And we start by running an A star search, but only using the lazy estimate to compute the cost of edges. And we're going to choose the very best neighbor and going to evaluate it using the expensive to evaluate edge. And I'm going to denote this using a green region. OK? And now the algorithm is going to proceed. We're going to look at all the new neighbors of this edge, evaluate them using the efficient estimate. So we expand our orange region. We're going to choose the best neighbor, evaluate it using the expensive to evaluate edges, expand the green region, and proceed. The next step, in this case, the edge is going to be in collision. And what's interesting now is that there's no subtree emanating from this edge, so there's no rewiring operation. And this is because the distance between a node on the boundary of the green region and a node on the boundary of the orange region is always 1. So there's no subtree here. And this is how the algorithm proceeds. So let's look at the pros and cons. As I explained, there's no rewiring that we need to perform here. So if the lazy estimate guided us incorrectly, we don't need to correct the future, the estimated future. However, if you believe me that I said that LazySP is edge optimal, is the best we can hope for with respect to edge evaluations, then you also believe me that here we need to perform much more edge evaluations. So let's look at these two algorithms side by side and compare them using the notion of what we call a lazy look-ahead. A lazy look-ahead is the number of edges that the algorithm uses the lazy estimate to guide the search. And we can say that LazySP, the first algorithm that I described, has a lazy look-ahead of infinity. It basically is purely optimistic. It believes that the future can be predicted using the lazy estimate, and it lets it drive it completely. And this means that we perform the minimal number of edge evaluations. We prove that it's edge optimal. On the other hand, we know that we pay a huge price every time we're wrong, every time we found an edge to be in collision with respect to graph operations. Lazy A star lies on the other end of the spectrum. It has a one-step look ahead. This is the difference between the green region and the orange region that I mentioned. And this means that we need to perform much more edge evaluations. However, we're optimal with respect to rewiring operations. And when we put these two algorithms side by side, it's very natural to look at them as two instances of a family of algorithms parameterized by this lazy look ahead. And this is exactly what LRA star is. Before I describe lazy LRA star or lazy receding horizon A star, I want to mention two properties. The first is a theorem, which we can prove. And it states that the larger the look ahead, the alpha parameter that I mentioned, the fewer edges LRA star will have to evaluate. And this is natural. We know that lazy SP, which is on one end of the spectrum, is edge optimal. So if we plot the number of edges evaluated as a function of the lazy estimate, this means that we have a monotonically decreasing function, which is exactly what we wanted to capture. The second property, and this typically occurs, we show in some situations where this does not occur, is that the larger the look ahead, the more edges LRA star will have to rewire. And this means that the look ahead alpha is like a knob. It's a parameter that allows us to tune between edge evaluations and graph operations. So let's try to visualize what we do. And it performs exactly as you would expect. Again, the green region is the area where we used the expensive to compute edge evaluations. And the orange region is the region where we used the lazy estimate. In this case, between a node on the boundary of the green region and a node on the boundary of the orange region, there's 3 edges. So I'm visualizing this for an alpha equals 3. And the algorithm proceeds as follows. We start by computing the best path, the most promising path, and evaluate the first edge along this path. In this case, we found it to be in collision. And we know that all of this subtree is incorrect. Now, in contrast to lazy SP, where we had a massive tree that we had to rewire, in this case, we have this nice property where we can bound the amount of work that we need to do because we know the depth of the subtree. It's exactly 2, or alpha minus 1 in the general case. So we can bound the amount of graph operations that we'll have to perform. So once we found this edge to be in collision, the orange region collapses, the green region expands a bit. We're going to choose the next best promising path. Evaluate the first edge. In this case, it's collision-free, so we can expand the green region. Now the depth of this subtree is only 2, so we need to expand the orange region. And I want to emphasize that this is done using the lazy estimate. So this is a very cheap operation computationally. And that's the algorithm. So it's a very natural extension of the 2 algorithms that I just described. Now if we plot this, this is a picture of a video of Herb running our algorithm and computing the shortest path. And let's look at this plot where we plotted the time as a function of the lazy look ahead. The first thing I want to show is the time spent on edge evaluations. And the time spent on edge evaluations, we can see that it's a monotonically decreasing function. And I want to emphasize that for alpha equals 1, this is exactly lazy A star, the first algorithm that I mentioned. Alpha equals infinity, or in this case 15, is lazy SP. The second plot is the green one, which is the time spent on graph operations or rewiring. And this is, roughly speaking, a monotonically increasing function. And what we actually care about is neither. What we care about is the total planning time, which is the sum of the blue and the green plots. And what we can see that there's an optimal value of an intermediate look ahead, in this case 5, which allows to balance edge evaluations and graph operations and produces the minimal planning time. As an aside, the whole motivation for this work or for this talk was stating that classical or traditional tools are unsuitable for this domain. Running A star is several orders of magnitude larger than using our algorithm in order to find the optimal path for this case. So just to summarize, we had this general path planning problem, which we could have solved using general tools. And we pinpointed what is the computational bottleneck. In this case, it was expensive edge evaluations. But we also had this additional tool of having a lower bound on the true cost. And this allows us to introduce a new search algorithm that balances these two operations. Yeah?
But the edge evaluations, they are in a sense part of the pre-processing, because if you now want to find a path from a third point to a fourth point, then you can reuse these edge evaluations.
So that's a great question, and I'm not telling the whole story, obviously. And we can use this approach even if we want to do a one-shot algorithm. So I'm giving you a graph, I throw a bunch of points, I connect them, and now I only want to solve one query. And in this case, you're right that that's a great question on how do we compute if we want to perform multiple queries on the same graphs. How do we not choose the best path, but maybe choose paths that we reuse edges evaluated from previous iterations in order to optimize for multiple queries? And that's something that we're actually working on at the moment. But this is a different question. If we have one query, I'm giving you a graph which was constructed lazily, meaning no edge evaluations. How do we find the best solution as fast as possible?
Yeah, but usually you don't want just one path, right? So after the robot moved her hand above the table, presumably she would want to do something else, right?
If the robot also moves, so the whole environment changes, so we can't reuse. So if I'm moving from here to there, I can't reuse data from the previous environment. The notion of reusing data and reusing computation is a theme that we're working on over and over again. And it's a valid point that we need, that it needs to be addressed. Specifically for this work, we had a new query every time.
Does it make sense to do a bi-directional search, both from the start and from the end?
There's been a lot of work on bidirectional search, both in the search community and in the motion planning community. And a lot of times, it helps. We can show specific cases where this does not help. And this algorithm is naturally extended to the bidirectional case. You need to understand the details if you're doing front-to-front, but you can apply the same algorithmic tools to a bidirectional search. This work, we wanted to put emphasis on the theoretical properties and prove what are the conditions and how does this allow us to balance between the two operations. But once you have this meta tool, then you can apply all the standard tools that we have to this meta tool. Okay, with this I want to move to some specific robotic domains. So this was in the abstract of a specific domain, and look at some of the challenges that arise in these domains. The first one I want to talk about is humanoid robots. This is one robot that I've been working on a bit. It's Warek, a humanoid robot with 34 degrees of freedom. And a very interesting question that arises in this domain is how to guide the search. Typically what researchers do is subdivide the planning problem into planning for the footstep motions of the robot, and then have a full body planner track those footstep motions. And because this is a high-dimensional system, a common problem that arises, or challenges that arise, is how to guide the planner. In the context of A-star-like planners, what's a good heuristic that estimates the cost to reach a goal from a specific node? Because of the dimensionality of the system and the specific constraints, this is very hard to hard code. And we've done some work on planning for the footstep motions of the planner. This is guiding a 6-dimensional space. So we have 2 feet. Each foot has a position orientation. That's 3 degrees of freedom. And here we used topologic characteristics from the workspace. And once we have these planners, the question is how to guide the full body planner. This is a video of the robot trying to climb stairs. And it gets stuck because the planner planned with the arms below the railings. And what we've done in this work is try to identify in a systematic manner when the planner gets stuck. So this is domain agnostic, how to identify when a A-star-like planner gets stuck. And then once we do, ask the user for guidance and how to automatically incorporate this guidance into the planning algorithm while having all the guarantees that we want for a planner. A different domain comes from the domain of assistive robots. This is the robot that I've been working on where we have a wheelchair and a standard robotic arm mounted to the wheelchair. And this is given for users with disabilities. And there's some what's called shared autonomy here, where both the user and the robot control the motion of the robotic arm. And we had a very interesting problem where some of the configurations were like this, where from the viewpoint of a user, remember he cannot move his head, the end effector, the gripper of the robot, and the tool we're trying to operate are visible. However, the planning system also planned for these types of configurations where the end effector is occluded from the viewpoint of the user. And we wanted to avoid these types of situations, but have this as a soft constraint. So we didn't want to completely tell the system that these are invalid situations, because sometimes you have to go through them, and sometimes they create paths which are much shorter and much more natural. So we wanted to penalize them. So the big problem here was how to model this problem. And the model here was that we want to penalize exposure to risk. I call a situation where the end effector is not visible to the user as a risky configuration. So we want to penalize exposure to risk in a superlinear fashion. And I'll explain this using an analogy. I have a 2-year-old daughter. And she's at a point where I can leave her playing alone in the living room. And if I don't look at her for 6 10-second intervals, everything's fine, and my living room is roughly the same mess as it was when she entered the living room. If I don't look at her for a minute, my living room's a mess. So the same exposure time of a minute, if it's continuous, we want to penalize in a superlinear fashion. And exactly we have the same problem here. So we have the problem of modeling the cost function. And once we modeled this and we had this superlinear penalty, we realized that standard graph algorithms cannot be used here because this cost function does not, the Bellman condition does not apply to this cost function. And this relates to your question. So we had to introduce a new graph planning algorithm tailored to this specific problem in order to solve this efficiently. The final domain-specific problem that I want to introduce is how to plan giving some task-specific constraints. This is Chimp, the CMU robot that participated in the DARPA challenge. Oops, sorry. And here he has a tool in his arm, and he needs to follow some predefined motion for this tool. And what the problem that we're trying to do here is following a task in what's called task space. The task space is the space describing all the poses of the end effector of the robot. So this is usually the position and orientation of the end effector of the robot. And informally, we're given some reference path in task space, and we want to compute a path in the configuration space, a path for the robot's joints, that follows this path as closely as possible. Why as closely as possible? Because sometimes we can't exactly follow this path. So let's try to understand this problem. We're given some path, and let's look at one point along this path. This is in task space. And this corresponds to a placement of the robot's end effector. So this is what I call task space. Now, this position of the robot corresponds to one specific point in the configuration space. However, for the same task space position, we can move the robot's joints while having the end effector at the same point. So we have multiple configurations corresponding to the same task space point. And we can move between task space and configuration space using two primitive operations, what's called forward kinematics, where given one configuration, we compute the task space point corresponding to that configuration. This is a one-to-one mapping. And what's called inverse kinematics, where given some task space position, we compute all the sets of points that correspond to that task space. And this is a one-to-many mapping. Now that we understand the problem, this is the right formulation. We're given some reference path, and we want to compute a path in the configuration space whose forward kinematics, when we map it to task space, is as close as possible to the reference path. And we need to answer A, what does it mean as close as possible? And B, how do we optimize for this problem? And the first question is pretty standard if you know a bit of computational geometry. And we're going to use the discrete Fauché distance. It's very natural in this context. So I'm going to briefly describe what this means. Let's assume that we discretized each one of these paths. And we're going to explain this using a standard analogy of a man walking its dog. So we have a man on the reference path. And we have a dog on the second path that we want to see how close is it to the reference path. And they're connected with a leash. And the dog moves along his path, going back and forth because dogs are crazy. And the man wants to also proceed along his path. And they always need to be connected using this leash. And the question that we need to ask is, what is the shortest leash that the man needs to leave his house so he can always be connected to this dog? This is a discrete Fauché distance. So how do we measure distances? Using standard tools from computational geometry, using the discrete Fauché. Now that we optimized that we understood the problem, how do we look at this minimization problem? So let's look at the first approach. This was the standard approach before we introduced our algorithm. And this is the reference path in task space. And what we're going to do is we're going to sample, say, the beginning and end or intermediate points along this task space path. We're going to compute an inverse kinematic solution, a configuration that corresponds to that task for each one of these samples, and interpolate between the two. And if we need to refine the samples, we can also do this. So we sampled the beginning of the reference path, and this is the IK solution, and the end of the reference path, and then we're going to interpolate between the two. And we're following the task space path, and it looks great. However, if our IK solution returned a different configuration, now if we try to interpolate between these two configurations, we're going to get a path that deviates significantly from this task space path. So the question is, this is not the best algorithm. We can see why. Let's look at some alternatives. Again, this is the path in reference in task space, and we're going to discretize it. What we did in the previous solution, we computed one IK for each of these waypoints, and we interpolated between them in the configuration space. And we understand why now the right thing to do is compute a set of multiple IK solutions for each one of these waypoints, and compute what's called a layered graph. So we connect each point to all points in the subsequent layers, and points within the same layer, so we can move from the same task space point within the configuration space. And now we have this layered graph, and we can redefine the problem as look at all paths in this layered graph. For each one, compute the forward kinematics, and ask what's the discrete Fauché distance to the reference path. And this again relates to your question, are the costs in the graph the sum of edges? No, here a cost corresponds to the whole path. So we can't apply A star or Dijkstra because we don't care about the individual costs of edges. If we have n as the number of layers and k as the maximum number of IK solutions, the number of paths here is exponential. So we don't want to iterate the paths, these different paths one by one. Again, by adapting tools from computational geometry and using that machinery, we can find this path in roughly quadratic time. This is the robot Herb, again, running our algorithm. Now notice that here the path corresponds to a motion that intersects the table. So we have to deviate from this path. And here I compared the first approach, which was the standard approach before we introduced our algorithm, with our approach, and we can get a much lower error much faster. With this, I want to move to future work. And I want to motivate this by a quote from a recent NSF-sponsored workshop on planning for robots in the real world. And one of the main themes, or one of the fundamental problems that was introduced in the introduction of a journal paper from this workshop, is that a lack of planning capability limits the range of tasks where currently deployed robot can be used. And there's a lot of domains where this is relevant to. The one I'm most excited to be starting to work on is the domain of robotic surgery, specifically minimally invasive robotic surgery. And obviously this domain has huge potential to reduce human errors, to reduce the recovery time, to decrease cost. And I'm going to demonstrate this using two systems. The first is the Da Vinci system, which many of you may be aware of. In this system, we have two parts. We have the robotic system, which operates over the patient, on the patient, and we have a console where the surgeon actually sits. And what the surgeon does is he teleoperates over this specific system. And this system has very limited autonomy, basically some motion scaling. So when the surgeon does a large motion, the system scales it down, and some tremor reduction. This is one example of these robotic systems for minimally invasive surgery. The second is what's called concentric tube. This is a video of these concentric tubes. These are typically a series of 3 or 4 currently tentacle-like medical devices. These are tubes which are pre-curved, and they're controlled by rotating each one of these individual tubes and translating them. And this is highly intuitive for surgeons. However, they can get into the snake-like motions, and they can allow to perform brain surgery by inserting them through the nasal cavities. They have the ability to reach areas and perform surgery. And this domain introduces a whole new abundance of challenges, from the fact that human anatomy is densely packed, so we need to have highly constrained planning capabilities. When we plan through the human body, then tissue moves, so we need to plan for deformable objects, for dynamic objects. Obviously, we have imprecise both medical imaging, and we have imprecise models of the robot, so we need to plan under uncertainty, and we need to account for planning for patient safety, and this is like the cost function that I talked about for the context of assistive robots. Now, this is a list of long-term 5, 10, 15 years challenges. To make this a bit more palatable, to ground immediate next steps, I want to talk about 2 specific works that I'm currently working on. The first one is moving from the domain of welding, which was the first motivation for task-based planning, to the context of tentacle-like robots. And the idea here, which we're currently working on together with Professor Ronald Turovich at UNC, is to have the surgeon state the path that he wants the end of the robot, so this corresponds to task space path, the end of the robot to take through the nasal cavity, and the surgeon does not know anything about the curvature constraints of the robot, if the action is even feasible or not. And we want to use our algorithm to follow these paths specified by the surgeon as closely as possible. Exactly using the same tool, but adapting them to this domain. A second example that I want to talk about is using procedure-specific simulations. This is for the Da Vinci system that I talked about. This is an image from a real surgery, and this is an image from these simulations. These are virtual reality engines where only the robot console exists and the robotic arm the surgeon's console exists and the robotic arm does not exist in these simple systems. And they're used to train surgeons to operate these systems. These are highly unintuitive systems for those who did not try to play around with them. It's embarrassing how you can look like playing with these systems. And currently, the metric used to evaluate surgeons are very, very simplistic. Basically, some binary classifiers. Did the operation succeed? Did he go below some specific time or not? Did he hit some anatomical areas? And what we want to do is use motion planning to compute a ground truth and then use this to evaluate users' performance. Now, these are 2 examples of immediate next steps towards this application. I want to summarize by restating that robotic applications, just like the one is minimal invasive surgery, introduce a whole new set of computational challenges. And they require exactly what I've been talking about all along this talk, revisiting traditional tools that were developed in the absence of these domains in order to adequately solve these types of problems. Thank you very much.
Let me start with a question.
Okay.
You said that you're planning for a humanoid robot, distinguish between footsteps and body movements. Aren't there any algorithms that combine, that do a more holistic approach?
There are. I'm not, usually they're more complex. What typically they do is do a whole body planner for a specific type, and they're more control based. So if we know that the humanoid needs to climb a ladder, this is a very repetitive action that we can use control, move your hand until you grasp, and then you don't need the footstep planner. For walking and then following the footstep planner, this typically performs favorably because you can use this low-dimensional space to guide the high-dimensional system.
I have many more questions. Okay, we'll let someone else if they want to. Okay, then let's thank Oren again.
Thank you.